Hey everyone. It's pretty amazing to be back here at Uphill Conf and to show you my latest side project where I try to recreate maybe the most iconic car in television history right in the browser. Now, first some words about myself. My name is Nico. I'm a front-end developer, as you all heard. I live in Thun. I work here in Bern at K.I.T.T. There we provide digital finance solutions, mainly for Berner Kantonalbank. I'm also part of the Google Developer Experts program in two categories, in web technologies and also AI and machine learning. And that means I just spend a lot of my free time just playing around with all kinds of new web APIs, browser APIs, and everything that's happening in the on-device AI world right now. So let's start with the question, who is K.I.T.T? So K.I.T.T is short for Knight Industries 2000, and it's an advanced AI-powered car from this TV series from the 80s. So the whole series is this good guys versus bad guys. So Michael Knight, or K.I.T.T assists Michael Knight in solving the cases and all of that. So in the end, K.I.T.T is a supercomputer, it's a car, it's a person, it's something between. Maybe we should rephrase the question, what is K.I.T.T? And in the 1980s, it was quite easy, because back then, K.I.T.T was just a super intelligent computer doing super intelligent computer stuff. Easy. But then we learned about machine learning. So we have artificial neural networks. They learn by changing the weights between neurons. So maybe it's just a huge artificial neural network. But now we are in the age of AI. And now I have a way simpler explanation. Maybe K.I.T.T is just an AI agent that connects different services with a decision-making process. Sounds easy, makes sense. Let's try to build it. Now, if we want to build it, we need to look into the features. What are the features that make K.I.T.T human-like? First of all, it listens and it talks. So we can talk to it in natural language. Then it's intelligent, so it can process information. It's not only just a soulless machine, it actually has a personality. It has a history, so we can talk to K.I.T.T about things that happened in the past. And last but not least, it has a body, so it lives in the physical world. So to solve all of that, we need a lot of machine learning. And I am a front-end developer, so I wanted to see if we can solve all of that in JavaScript in the browser. And we can use machine learning in JavaScript in the browser, but to do that, we need three things. We need hardware and access to the hardware. We need libraries to interact with the models, and we need the models themselves. So let's start with the hardware. We can actually use the CPU in the browser with JavaScript or with WebAssembly out of the box, but that's not very performant. If we want to have performant machine learning operations, we want to use the GPU, and there are two ways to access the GPU. We can use WebGL, which is this graphical abstraction layer, or we can use a rather new API, the WebGPU API. And there is even a newer API, WebNN, and that's now a work in progress, I would say. And there the idea is that we have GPUs in our devices, but you also have, my phone, for example, has the tensor processing unit, the TPU. The new Windows laptops have an NPU, the neural processing unit. So the WebNN is an API that tries to give this one abstraction layer where the operating system decides what a processing unit they should use to run machine learning operations. So once we have the hardware, we have to look at frameworks or libraries. And last year, I did talk a lot about TensorFlow.js. And this year, I had to do a lot of natural language processing, and there's another library that I use very extensively for this talk, and that is Transformers.js. Transformers.js was released in 2021 by Joshua Lochner, who is better known by his handle Zenova. He then joined Hugging Face, so the whole project is now part of the Hugging Face family. It's designed to be pretty close to the Transformers Python library, and it stands on the shoulder of giants, so it uses the Open Neural Network Exchange standard. So there's this Onyx runtime web that they use under the hood to then run the models. To use Transformers.js, we can import this pipeline operator from Transformers.js. We can then create a pipe with a task and a model, and there's a list of tasks and models that we can use. And when this code runs, it will first download the model from the source, wherever that is. You can then show a progress callback if you want to. You can then decide whether you want to use WebGPU or the CPU, and you can also define the compression type of the model that you want to use. And what it does is it basically takes any input, takes that, runs it through the model, and then returns the output. So in the end, the input and the output types are heavily dependent on the task and the model that you are going to use. So let's see how we can use Transformers.js to solve the first thing. We want to talk to K.I.T.T in natural language. First of all, we need to transcribe text. And there's a model family called the Whisper models that we can use with Transformers.js. So we can create this transcriber with the automatic speech recognition pipeline. We can then pass the model is the Whisper Tiny under the Zenova handle on Hugging Face. And then once we have the transcriber, we can pass any audio to the describer and it will return the output as text. On the other end, we can use a rather new model, and that is Kokoro. And Kokoro.js is also written by Zenova, by Joshua Lochner. So basically, it's just a small abstraction layer on top of Transformers.js. And here we can create this TTS function. Then we can call TTS.generate with any text. We can define a voice, and it will then return the audio blob. So let's try it out. I have a little pipeline here. It should record everything. It should transcribe it, synthesize it, and it will then output everything. So I hope the audio will work. Hey everyone, I'm right now at Uphill Conf. It's an amazing conference, and I'm super happy to be here.
Hey everyone, I'm Red now at Uphill Conf. It's an amazing conference, and I'm super happy to be here.
Okay, that works. But there's one crucial thing missing. It's not actually intelligent. So what could we do to add intelligence to this pipeline? So the closest thing we have to intelligence right now is LLMs. So we have large language models. And there is a whole bunch of language models that we use. So most of us probably use the ones in the upper left corner. So there's GPT-4, there's Gemini, there's Claude. So those are the big ones that we use over an API. But there are also smaller ones, like the Gemini Nano and the GPT-4o Mini, and they are small enough that we can even run them on device, because they're less than 5 or 10 billion parameters. The problem here is they are closed, so they were trained by OpenAI or Google or whatever, and we can use them via an API key or via a chat interface, but we can't run them on our devices. But there's another group of models, and those are open models. And open means that the trained weights and also the architecture is open. So there are big ones like the Llama 4 Behemoth or the DeepSeek. And there are also smaller ones. And there's a whole bunch of small models that are open and even small enough that we can run them on our device. And I am super sorry that I didn't include small LM. And the first thing I will do is I will add small. First of all, I will try it and I will add it to the slides. But for now, it's mostly like the Mistra 7B, there's the Phi and the Gemma family. And just a month ago, Google released the Gemma 3 1B, so there's just a 1 billion parameter LLM that we can use. And since we have WebGPU, we can even run them in the browser. And I think you already heard about that a little bit. The library or the framework that I use to do that is called WebLLM. With WebLLM, we can basically create an engine where we can pass the ID to the model that we want to use. There is a list of models pre-configured from WebLLM that we can use. And when this code runs, it will first of all download the whole model to the application storage. So it takes a couple of minutes. But once it's downloaded, we can create a conversation. In a conversation, we first have a system prompt that sets the scene, and then we have a user query. And when this code runs, we can then either wait for the full response, or we could use streaming, so it will then just add tokens as they are generated. So let's see how that looks. I have a prompt here, and I can say, who are you? And it will then take some time, but it will generate an answer. I'm Gemma, an AI assistant. And what you can see is that it's actually quite fast on my MacBook. So it processes the input tokens at around 70 tokens per second. And to then generate the output tokens, it can do that at 32 tokens per second, which is quite fast, I would say. So Let's add that to our pipeline. We have a new step, and that's the processing part. Let's try that. Hey there, my name is Nico. I'm right now at Uphill Conf. It's an amazing conference, and we are on stage right now. So could you quickly introduce yourself to the audience?
Hi everyone, I'm Gemma. It's great to be here at Apple Conf. Sparkles.
Okay. It's not actually Apple Conf, but we'll get to that later. So now what we have is a pipeline that we can talk to the model, but there's one problem. We just created another random chatbot because I wanted to talk to K.I.T.T and not to Gemma, that it was just a random Gemma model that was trained by Google. So how can we fine-tune a model? How can we change the model to our needs in the end? So to fine-tune a model, we can... Oh, yeah. I'm pretty sure we're going... Yeah, we did talk. I mean, just show me the slides for the fine-tuning. You don't need to be mean, but and there's an easier but super effective way. Maybe it is talking about prompt engineering. So yes, it is. So prompt engineering is a way easier process. So prompt engineering basically means it's the process of crafting precise and effective input prompts to optimize the output of AI models. So what does that mean in my case? So what I can do is I can take the exact same pipeline, but now I have a different system prompt. And in the system prompt, I give it some context. I tell it, hey, you're a kid from Knight Rider, speaking car, talks with Nico, so it has more context. I have some guardrails, keep your answers short. And then I have a whole summary of K.I.T.'s tone and some more guardrails because I don't want to have the whole smiling faces stuff. So let's try the exact same model with a different system prompt. Hey there, I'm right now at Uphill Conf. It's an amazing conference, and we are on stage right now, so could you quickly introduce yourself to the audience?
Understood. Your current location is being mirrored in the studio. Please provide the challenging code snippet. Keen to work through a rehearsed code scenario.
Okay, it's still the exact same pipeline, it's the same model, but the output is very, very different. But let's talk about memories. And in the case of K.I.T.T, we have a lot of memories. There's so many things that happened in K.I.T.'s past. So what could we do to access those memories? And the next couple of slides, they open up a huge rabbit hole, and I try to keep it as short as possible. But if you want to do it yourself, you might want to go to Reddit. There will be a subreddit of your favorite show. There will be someone who has a link to a website where you find all the screenplays in plain text. You will then write a little playwright script that parses all the screenplays, so you have them on your device in plain text again. Then you will figure out that those screenplays were written in pre-World Wide Web times, so you have to write your own little parser that parses the screenplays into structured JSON, and then you're done. Now you have your 6,275 scenes in 432 acts in 48 episodes that you can add to your database. And in my case, it is just the IndexedDB, which is a document database that lives in the browser. Now what? Let's imagine we want to know something about something that happened in the past. I have one question, one query. Now, how can my LLM know what's the scene that I am referring to? So the easiest way to do that is to use similarity search. And I actually have a couple of slides that explain similarity search. But after Louis' talk in the morning, I will just skip through those slides because the way he described it was just pretty perfect. So we can just go to this one. In the end, similarity search is basically everything that can be represented as a vector can be compared for similarity. Now, how can we use similarity search in the browser? There's another model family called the feature extraction models, and we can use, for example, the all-mini LM L6 v2, and that is a model that was trained for similarity or semantic similarity. And with this extractor, we can pass any text to the extractor, and it will return an array of 384 numbers. That means, in the end, we have two strings. We have hello people from the capital of Switzerland, and we have good afternoon developers from Bern. Two strings with a very similar meaning, but very few shared words. And if I change Bern to Thun, for example, you can see that the similarity score dropped from 0.69 to 0.61. Thun and the capital of Switzerland is still close together, but not as close as Bern and the capital of Switzerland. Okay, so we have similarity search, but now we have another problem. Because those screenplays or those scenes, some scenes are just multiple conversations, multiple plots, and some are just one-liners. So how can I convert all those scenes into small summaries that I could then use for similarity search? The solution I came up with was to use this LLM summarizer. And the LLM summarizer is, again, just a large language model that has a system prompt. Or no, first of all, I calculate how many plots do I expect. So longer scenes have maybe 4 or 5 plots. Short scenes have just 1 plot. Then I tell it, hey, you are an helpful assistant. I have system prompt. And then I have a very strict prompt where I have some instructions. It should find the main plot lines, maximum, max plots. And I'm also very strict about the output format. So it should return a JSON array with all the summaries as strings. So I have my summarizer. And I was then able to summarize all those 6,275 scenes. And to do that, on my MacBook here, it had to process 3.1 million input tokens to then output 303,000 output tokens. I did it locally on my MacBook. It did take a couple of days. It did crash sometimes, but I was actually able to do that. Now, that also means I was able to create a vector search function. Now, IndexedDB is not actually a vector database. But in the end, everything is a vector database if you can store the thing that you want to represent, and it's vector. So what I was able to do is I would just get all the entries, all the scenes from the database. I would then filter them, or first of all, I calculate the cosine similarity between the query and the summary, and I will then return the 4 scenes with the highest similarity to my query. That's basically it. So I have my function. Now, how can I call this function in the LLM workflow? And that's a concept called function calling. Pretty sure you heard about that. In the end, an LLM cannot execute a function, but the application around it can do that. The LLM can detect when a function should be called. It can generate structured output. Could be text, XML, or JSON. By the way, I am using XML every time I do have structured output or structured input for LLMs, because for the small LLMs, it works way better than JSON, because with JSON, there's just too many errors that could happen if there's just a parenthesis is wrong or a comma is wrong, and it can just not parse. So therefore, I'm always using XML. And the application can then execute the function. It will return the output back to the conversation, and the LLM can then process that in the next step. Now, there are frameworks that we can use, but if you use frameworks, where's the fun, right? And I also wanted to see how it actually works under the hood. So I tried to implement function calling with just basic LLM text in, text out. And the function, or maybe called function that I came up with, looks a little bit like this. So you have a system prompt, and in the system prompt, I tell it, hey, you are a kid from K.I.T.T, you have memory recall capabilities. You can call the function find memories, and then I'm strict about if you want to call a function, use this function call XML with the name of the function and then the parameters. I have some instructions, I have some examples, because LLMs, they love example code. And then I just have my user query. Okay, what we just implemented is RAG, Retrieval-Augmented Generation. But if we are very specific, it's actually agentic RAG, because the LLM, in fact, decides if it wants to use this RAG approach. And if you're talking about buzzwords, that's also what an AI agent is. It's a program that autonomously completes tasks or makes decisions based on data. Okay, let's try. We can now go to kit.nico.dev. There we go. And we can wake up. Now, whenever I press the space bar, it will actually listen to what I say, and it will then parse my query. So I can just say, "Good morning, Kit. How are you today?" And we can see the log as well.
Good morning, Nico. I am operational and ready for whatever task you have for me.
So that's just a very simple question that it can answer without calling any functions. But let's try something more. Hey, do you remember the connection between Sonny and the deadly poison gas exchange? And did something tragic happen back then?
Let me see if I can find something about that. It's a bit of a long shot, but I'm not entirely sure if that's something I've encountered before. K.I.T.'s programming was tampered with, leading to his consciousness being transferred into a portable television set. He was then used to investigate a crime.
Okay, that's not exactly what I was expecting, but we can still look into what happened, because you see that's the whole system prompt. And in the system prompt, first of all, your Kit from Knight Rider, the summary of Kit's tone and all of that. Then I have a list of all the tools, and search episode is one of the tools that it can use. It then uses that tool because it adds this little function call XML snippet with search episode, with the parameters and all of that. And then it does actually execute the function. So it will first parse this thing. It sees, okay, there's a search episode that I need to call. It will then return the results from the function as a new message in the chat or in the conversation. And now it has some context to answer the question. So what it's then able to do is it's able to answer the question based on the new context that I was able to provide. Okay, that was basically the first part, because I also wanted it to give it some body, some physical form. So I did look at some Pontiac Firebird, but the thing is that they are more than 20,000 Swiss francs, and believe it or not, that's not in my budget for side projects. And also, I'm not a mechanic, so I had no idea how to deal with a car, but I'm still a kid at heart, so I was able to create this little Lego kit that should work as my car. But now I have a new problem, because I have this Lego car and I have my web application, so how can I communicate with the car from the web application? And there is an API that you can use for that called WebBluetooth, and that is a way to communicate with Bluetooth low energy devices from the browser. The way it works basically is that you have this generic attribute profile. There you have a K.I.T.T server. A server has some services. Each service has a list of characteristics, and each characteristic then identifies a value and also defines what operations can be performed on that value. And each value is then just an array of bytes. And on the right-hand side, you can see the JSON schema of the K.I.T.T server of this playbulb sphere. And what you can see is we have services, characteristics, each as UUIDs. And on the bottom there, you have the service or the characteristic for the light service in the end. And there you can see we have 4 bytes, and each byte represents the intensity of one of the LEDs in this playbulb sphere. So we have a white LED, red LED, a green LED, and a blue LED. If you want to use WebBluetooth, we first have to connect with a device. In that case, I want to connect to the playbulb sphere. Once we have the device, we can connect to the service, to the characteristic. And on the characteristic, we are then able to read the value, or we can also write a new value, which is a unit 8 array, just the new values for R, G, and B. So let's see how that works. We can now connect to the playbulb sphere. There we go. And what we can do is we can then send commands to this light bulb, and it should then change the color based on the new values that I sent from the browser to my playbulb. Now, I wanted to see if I can use that in an agentic workflow. So I have a new demo. I need to connect again. And here, I still have basically the same pipeline as before, but now I have a different system prompt. I have you are a bulby, an intelligent talking light bulb. You can change the color. That's the function call, change color with a new hex value. some instructions, some examples, and some context, so it knows what color it has right now. And here I have a new function call which parses the output. It will then call the function and it will execute the function. Let's try that. Hey Balbi, could you show me your favorite color given it's not the same that you have right now?
I'm not sure what would be Bobby's favorite color. I'd like to learn how to choose my own.
Okay, but it actually changed, or the LLM actually changed the color of my light bulb. But let's get back to my car. So my car, in the end, is an Arduino Nano RP2040, so it's an Arduino microcontroller board. It has a Bluetooth strip on the board. It's connected to this little LED strip and to the wheels. And on the board, I then have a very basic C++ program that just exposes one BLE server with one service and one characteristic. And that characteristic has 2 bytes. And each byte controls the speed of one side of the car. So I can change one value for the right-hand side and one value for the left-hand side. And that's all it does on the car here. So let's get back to K.I.T.T. There we go. And I can now turn it on. I have this amazing switch here that works as well. So I can connect to the car, hopefully. So it is blinking, there we go. And I can now use arrow keys, so I can just use arrow keys to change the speed of those wheels. I can also try it on the floor here. I'm sorry that not everyone is able to see it, but we can use just arrow keys and it will drive around. There we go. But now, how can we use it in this agentic workflow? So we can, for example, say, hey K.I.T.T, we have a problem. I think we need to get out of here. Could you go full speed forward?
We need to get out of here quickly. Let's go full speed forward. Let's go.
So what you can see is that it actually tried or did change the speed here. And there's also a very funny thing, because what I figured out is that, as you can see here, it calls the function change speed, and it does that. And then later on, it tries to call the same function again. And that is just something that happens with small models. And I have no idea why, because in the system prompt, I explicitly told it that if it already executed the function, it should not call the function again. But I think those small models just have some drawbacks. So you have to be a little more creative in your application. So in my case, for example, I just have a log of all the functions it already called. And if the function has already been called once, it should not execute that function again. So if you're using small models, you just need to be more cautious about the application around your LLM. But we can also do, let's say, more. I mean, that's just basically, if I can say full speed forward. And last year, I had some voice recognition where my slides recognized when I said certain words. So I could have used the same thing for this again, but I actually wanted it to have some more reasoning capabilities. So I wanted it to actually understand what it has to do and then to try to react on what I said. So if you have a more complex thing like, hey K.I.T.T, we have a problem. There is a roadblock in front of us, and on the right-hand side there is a river, so we can't go right either. What should we do next?
We need to find a way to maneuver around the roadblock. A left turn might be the best option. I've turned left to avoid the roadblock.
Okay, it actually works. So we are able to create K.I.T.T in the browser. It listens and it talks using Whisper and Kokoro with Transformers.js. It is intelligent using the Gemma 2 LLM. It has a personality using just prompt engineering. It has a history using all the scenes from Knight Rider and Agentic RAG. And last but not least, it has a body. It's using WebBluetooth to communicate with the car itself and function calling. Now, we know what I did. We also know how I did it. And the big question is now, why? Why should I spend hours working on a car from a TV series that I didn't even look as a kid? And the answer is pretty simple. It's just out of curiosity. Because when I started as a developer, I was around 13, 14 years old. We had a band, we needed a website, so someone had to learn this Microsoft front page. And little side note, having a band as a teenager, it has always been a dream of mine to be on the Gordon on stage. So it's not exactly how I imagined it to be, but it's pretty close, I would say. But back to the story. I mean, now I work as a programmer, and I still like it quite much. But there's always those times where you get back the issue that you worked on for days already, and it's still not the way testing or your client expected it to be. And those are the moments where programming actually feels like work. And in those moments, I'm super happy to have my side project where I can just follow my curiosity. I learn a ton of new stuff, and it's just fun to build those things. Now, why the browser? Well, again, I started in the browser, and I was amazed that I can just write some HTML, some CSS, I can upload it to some server, and people are able to access it, they're able to interact with the thing I built. And therefore, it's just amazing how well the browser works, how well the whole system works. And it doesn't stop with just HTML and CSS. You also have JavaScript. We have a whole set of browser APIs that we can just use out of the box. We have, again, WebBluetooth, we have WebNFC, we have WebAudio. There's so many APIs that we can just use. They're just there for us to use. And now we have LLMs. We have AI, and right now AI is just a new tool, a tool that we can add to our toolbox to start building cool stuff. So, thank you so much for your attention. It was great to be here.